used to having intro Gen Chem labs on Thursdays, so sometimes I get it mixed up. It's not like Thursday, no, you guys have Tuesdays. So honestly, we need to get down the road sufficiently in the material for Tuesday's lab to work for us. And when I say Tuesday, I don't mean next week. I mean the next week, the week after spring break, okay?
Which is our spring.
Oh, man. Well, gotta be somewhere. And did you say here? When was that? What days? We shall carry on. 18th is our third. What days are we?
I think it's a Saturday to Saturday.
Wow. This is so rude of me, but I'll just say what goes through my mind as a teacher. It sucks to be you. Because with this class, we're just gonna keep, we aren't gonna tear through each other, but we're gonna, that's one of the differences the college class usually versus high school. So I do record videos, so you'll have access to those.
I can send you the notes.
And so, yeah, it'll be kind of tricky. All right. So I like, this class keeps building on itself. Now we've talked a lot about atoms. Now we're going to stick the atoms together to make compounds. So this is exciting. So a compound means you have atoms of at least two elements, if not more, that are stuck together. And a repeating unit, actually, of a compound, we're going to use the word molecule, like a water molecule. But if it's a different type of compound, ionic compound, we're going to call that repeating unit, forming unit. So hold that thought. We can go ahead and take a compound and tease out the elements by some sort of just ordinary chemical means. The opposite of ordinary means would be some sort of nuclear reaction. You don't have to do a nuclear reaction to take a water molecule and break it down to hydrogen molecules. Just some sort of chemical reaction will break down all compounds into simpler forms, if not all the way to their elements. Okay. This last one up here kind of reminds me, remember we talked about Hofbernickel, where each letter in that last name stands for an element. Okay, where if I put little twos here, actually, I'm telling you that those are diatomic elements. Now, those actually are diatomic elements, and they actually a molecule of those elements, but those are not compounds. The reason those aren't compounds is you have to have atoms of at least two different elements, if not more, that are stuck together in that repeating unit. So, makes sense. And a lot to fill into this slide. Hand slide. Okay, so for instance, the formula for water is H2O. That means in the repeating unit there are two hydrogens and one oxygen. We in chemistry we deal a lot with water for a number of reasons. It's very available. It's a wonderful solvent, and life needs it. So H2O looks like this, where we have, actually the oxygen is going to be in the middle, and these lines right here are the chemical bonds we're going to be talking about, and so that kind of is what we call a water molecule. Carbon dioxide, CO2. This is a good example of you need to make sure your oxygen is capitalized, otherwise it'd be cobalt. Ethane has carbon and hydrogen in it. Specifically, it has 2 carbons and 6 hydrogens in the molecule. Calcium sulfate, CaSO4. Now, when you see a chemical formula for a compound written this way, you have to kind of think of, and I just talked about this in my physical science class, you have to think of this 2 as meaning that I have 2 of these groups that it is actually after. So these parentheses, I have 2 NH4 groups. So that means it kind of looks like this. If I have NH4 quantity 2, S, I have that sulfur in the middle, and I have 2 NH4 groups. So here's one NH4 group, and here's one NH4 group, where all of those dashes are chemical bonds keeping those. Let's see, how many atoms do we have? So we have 5 atoms in here, 2 of those, so that's 10 atoms plus 1 atom. Those 11 atoms stuck together with those dashes. Similarly, magnesium nitrate, where I must have 2 of these NO3s, we call it nitrate groups. All right. And you probably buy this, H2O, the formula for H2O is this, and it's understood that even though there's not a 1 there, if there's nothing there, it means 1 by default. We do that a lot in chemistry. So you may or may not know this next part, and it's somewhat subtle difference, but it has important ramifications. When we talk about a compound, there's 2 types of compounds, and if you get this in your notes, I'm going to actually kind of build on the board columns, 2 columns, and I'm going to call the left column molecular compounds, and I'm going to call the right column ionic compounds. So molecular, my abbreviation for compounds is CPD, and ionic. Let's kind of compare and contrast the 2. Now, what they have in common is we have at least 2 different elements or more that are stuck together in a repeating unit, and we use a formula to describe what that repeating unit is in both cases. But there are some important differences. This one is a subtle difference, but I mentioned a little bit ago that the word molecule or formula unit, if we have one repeating unit, of a molecular compound, we would call that a bona fide molecule. But I would argue that the word molecule probably is overused, because if you're being technically correct in the way chemists or physical scientists should use the terms, if you have 1 repeating unit of an ionic compound, 1 repeating unit, you can't call it a molecule because it's not. And I've heard people call it a molecule, but it's not. We're going to actually call that a formula unit. And we're going to see that ionic compounds are kind of a different cat when it comes to isolating 1. All right, so what else do we have? Again, something to kind of compare and contrast. In general, and this will go under ionic compounds, in general it says we have metals bonded with nonmetals. And I'm going to put it this way, especially when you contrast it to molecular compounds. Ionic compounds have at least 1 metal. There are some exceptions. 1 metal in the formula. And this kind of then piggybacks on what we spent some time in Unit 1 talking about. We have the JAG on the periodic table here, it's in red, and it separates the metals from the nonmetals. So if you have one of these in your formula, then odds are very high that that's the formula of a compound. That is an ionic compound. And then to contrast that, over molecular compounds, I'm going to say you have all nonmetals. All nonmetals in the formula. Now, I know it's like, are you serious? You're talking about the 3rd unit exam? I just took my 2nd unit exam. But on your 3rd unit exam, we'll talk more about this. I will actually give you lists of compounds and ask you, is that a compound that represents an ionic compound? Does it have a metal? Or is it a molecular compound? I mean, no metals. So, something to look forward to. Now, you guys, oh, sorry. I thought I had it on my slide, but I'll go ahead and tell you. On my periodic table, and actually, Caleb asked about it. Cole. His name's Cole, not Caleb. Cole is saying that I have hydrogen twice, and this is kind of why I have hydrogen twice, because it kind of sometimes behaves as a nonmetal, And sometimes it behaves as a metal. So that's correct. But for purposes of this discussion, and I'll put it under the non-metal part, or excuse me, on the molecular compound part, we will consider hydrogen a non-metal. If you have to identify a compound as being either molecular or ionic and it has hydrogen in it. These actually don't, these little videos don't move for me, but I'll try to kind of describe what they would do. There was no sound, but hydrazine has 2 nitrogens and 4 hydrogens. This actually, you can kind of see the ball and stick. The stick represents the bond. We have nitrogen, bond, nitrogen, and then we have those 4 hydrogens that are bonded to 2 hydrogens here, 2 hydrogens there. The thing about something that is a molecular compound is it is a nice little, we know that those, 6 atoms go together. And I'll kind of contrast this with ionic compounds. Similarly, I can't necessarily animate this one. Ammonia is the formula NH3, so the blue thing is the nitrogen and the white things are the 4 hydrogens. And there actually is a reason, we'll be talking about this later in the class, why it kind of those 3 hydrogens look like kind of legs, why they are kind of deflected away from the center. But again, I could go ahead and it's kind of like a magician who has their assistant is hovering in space. So the magician kind of takes their hand and goes all the way around the hovering assistant to kind of show you there's no strings attached. So there's ammonia, NH3, that we looked at a minute ago, and now you can kind of see, we'll be talking about why this is or where they came from, but you see the 3 hydrogens kind of deflected away from the top. That little thing up there that looks like eyes, that actually is a pair of electrons. They're called one lone pair of electrons. Water molecule, methane molecule. Again, no metals in these. So if you go ahead and consider hydrogen a non-metal, there's no metals in the formulas of these compounds. So they're all molecular compounds. So again, this is saying what I just said a minute ago, that basically if you have a molecule of a molecular compound, that's all you can have a molecule of, then we know those particular atoms are all stuck together in that repeating unit. So switching gears, why is an ionic compound, how is it different? And so to kind of set the stage, and we might watch these videos again later when we talk about the ionic bonds, but I'll put an example here. Example. You guys would probably tell me table salt is sodium chloride. The formula for sodium chloride is NaCl. I know that it's an ionic compound because if I find sodium, I can find it to the left of the jag. It's definitely a metal. Okay. An example over here, I usually say is water. But let's look at sodium chloride, how it's different in than a molecular compound. I think that's why it's like the magician. The magician can't like take a, so see, no, nothing connecting here. You're like, dude, it's like connected all the way around. It's like a commune instead of an individual sort of deal. This is just kind of showing you, there's this whole field of science called crystallography, and it deals with actually kind of what we're talking about these facets, these faces that ionic compounds in their solid states will form. So when you have kind of alternating cation, anion, it's just kind of a mess. For instance, with sodium chloride, if you go back and kind of look at the figures, you're going to see that each ion actually has 6 neighbors. So each cation has 6 anions, and each anion has, okay? So there's no specific pair that go together. So we call a repeating unit a formula unit. All right, so a little more, kind of compare and contrast. Let's see, how do I say this? Before I go on, I want to emphasize this. An ionic compound must have at least one metal, or in general, that's like 95% correct, because there are some exceptions. It can be an ionic compound with no metals. But the other thing, if it's an ionic compound, it must have at least one ionic bond. And I'll describe what an ionic bond here is in a minute. And if it is a molecular compound, then it needs to have all covalent bonds. And these bonds are what we say chemical bonds. So there's two types of chemical bonds. So the covalent bonds are electrons are shared. And I'm going to build on that in this unit 3, and I'll kind of talk you through what do we mean by sharing electrons. But I told you H2O is an example of a molecular compound. So when I draw these chemical bonds connecting the two hydrogens to the oxygens, this must be a covalent bond, and this must be an example where electrons are shared, and they totally are. Ionic bonds, we kind of saw the little video. So this right here, if I draw a sodium chloride formula unit, for some reason I usually show that chemical bond as a dot, 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 dot. I don't know why. But here's the one repeating unit, one formula unit of a sodium chloride. This actually must be an ionic bond. And like the slide says, ionic bonds are where electrons are transferred. Electrons are transferred. And we kind of saw that, well, we definitely saw that with that first video. Okay. Electrons are transferred, and what does it give you? Well, it gives you something that's short an electron or 2 or 3, which is what we call a cation, and it gives you something that has an excess. Okay. And then we have our dot, which we call anion, and then we have an ionic bond between those two. All right. So I kind of got ahead of myself, but I wanted to know that. So I've written this on the board already. Ionic compounds then must contain at least one ionic bond. At least one. It kind of contaminates the compound. There are a lot of compounds out there that have most of the bonds connecting the atoms actually are covalent bonds, but if you have even one ionic bond, it's an ionic compound. Covalent compounds, it contains only covalent bonds. Only electrons are shared. And actually, I think we've seen this on a slide or two or here, and I just mentioned it here in a minute when I kind of said chlorine picks up an electron to be like argon, sodium kicks off an electron to be like neon. Why transfer an electron, or why share an electron? And it has to do with getting that, what we say, complete octet, electrons like the rare gases. So, over here, oh my goodness, so molecular compound, I see I go back and forth. Molecular compound and covalent compound are the same thing. So I just think it's helpful seeing it all up at once. Okay, so in physical science we introduce a lot of Greek letters, and this is one such Greek letter. Actually, it is called chi. So electronegativity is chi. We introduced a Greek letter rho for density, and chi is for electronegativity. Okay, that looks like an X. Fancy X. Electronegativity is important because if I have atom A, my fists are atom A, and this fist is atom B, and I'm sticking them together with a chemical bond, okay, it's their electronegativity of these two atoms that kind of dictate that tug of war that's going to happen with that chemical bond, okay? How the electrons are going to be shared. Okay, so for instance, if atom A has a higher electronegativity, I'm actually going to see the thing that connects them. Actually, chemical bonds are, especially covalent chemical bonds, so you think of electrons as being present for that chemical bond. So electrons can be shared, but actually this atom A that has a higher electronegativity will get the lion's share of the electron cloud. This one will be kind of wimpier. This one will be stronger. Higher electronegativity means that actually it's going to try to hoard electrons to itself. And if we think of something that wants to hoard electrons to itself, we just actually talked about the extreme where chlorine wants to really hoard electrons. It wants to actually get an electron transferred to it. So the nonmetals have high chi's, high electronegativities, and the metals have low electronegativities, because we just saw that sodium and potassium want to kick off the electrons. You're like, dude, tug of war, you win. Okay. All right, so I moved the arrows around a little bit. So electronegativity must increase the closer you get to the nonmetals. And if you're in the same group, the way this works is electronegativity increases going up the group. So knowing the electronegativity or the general relative electronegativity of an atom tells the story of if that atom is bonded to another atom, will it want to pull electrons to it? Does it have a high electronegativity? Or will it want to kick electrons out? Does it have a low electronegativity? So I've got some slides kind of showing you about electronegativity values. So this 0.7 to 4, those are electronegativity values. Those are chi values. Sometimes electronegativity values are called Pauling values. Okay. So you can kind of see just for the group A elements, and actually the previous slide just said for the group A elements, we've got this S block and we've got the P block here minus the rare gases. The thing about the rare gases is they have three names: rare gases, noble gases, and inert gases. The idea that you're going to get that to, as your atom A to bond with atom B, is not happening because they are inert. So you can see the electronegativity increasing across the group and across the period from left to right, and electronegativity increasing as you go back from the bottom of the group up. So these are kind of showing you electronegativity values again. You can see in the group B elements, we kind of have kind of a little bit of a mixed bag with regard to the tug of war, trying to get electrons into themselves. And yet another slide. This is actually, if I'm doing some homework, trying to find out and I need an electronegativity value for an element, this is the slide I go to. This is my go-to slide for that, where these are the Pauling values. These are electronegativity values we've been talking about. It gets very high electronegativity values over here with the nonmetals and low electronegativity values here for the metals. They like to kick off electrons, low electronegativity values. The nonmetals like to take electrons in if given a chance. I'm going to put something on the slide, and I'm going to throw another Greek letter at you. I don't know very many Greek letters. But this triangle here, that actually is, I think, the lowercase delta. We call that delta. And in science, what that means is change in. Change in. Okay? So delta means change in. So if you have atom A and atom B bonded together, you might need to evaluate the electronegativity, what we say electronegativity difference between those two atoms. So the change in electronegativity value, so it's called actually delta chi, electronegativity difference. Change in electronegativity. If we think of a large difference in electronegativity values, what that means is, and I've been calling this atom A, and this has a high electronegativity value. If it's like crazy higher than this, then actually a large difference, like the slide says, means that an electron will be transferred from the one with the low chi, low electronegativity value, to the one with the high electronegativity value. And it's just like that animation you saw a little bit ago. If you have an electron transferred, okay, then you're going to form an ionic bond. And I'll go ahead and kind of show you. I have sodium chloride up here. The video we watched showed an electron transferred from the sodium to the chlorine, and in doing so, that made the chlorine a negative charge, and it made the sodium a positive charge. And like I said, we can think of in a correct way that it's that formation of two different oppositely charged ions that then creates that ionic bond. That's so cool. Well, if you're looking at atom A and atom B, and you're like, they're differences, but they're not crazy different. Then again, if I think of it as a tug of war, you're like, oh, well, then the electron is not going to be transferred because the difference isn't big enough. So electrons are going to be shared. But they aren't necessarily shared equally. But if they're shared and not transferred, then that's going to actually give us our covalent bonds. So if we go back to kind of that slide that I said, this is my go-to slide for electronegativity values, you could basically come up with any of the nonmetals. We can kind of pick on any of these chi, any of these electronegativity values, and come up with a delta chi electronegativity difference. And you're like, oh, that's not too much of a difference. Not so much electron's going to be transferred, so electron is going to be shared between those nonmetals. And actually, we've kind of come full circle to try to kind of connect the dots, so to speak. Okay, that's why nonmetals bonded to other nonmetals are covalent. But if we have atom A and atom B bonded together, and if we pick a metal, which has a low electronegativity, and we pick a nonmetal, which has a high electronegativity, you have set yourself up for an electron to be transferred. It just is. It just was. It just does. Okay, and that's actually why we say if you have any metal in your formula, you're going to have something that has a low electronegativity. It's going to kick off an electron to become a cation, and kicking off electron is going to create an anion. And then between those two, you have a positive and negative charge. Okay. So this is just kind of to summarize, and it's consistent with what I've kind of been building this morning. Metals bonded with nonmetals. If you have a metal in it, okay, that's going to be the situation, and it's going to give you an ionic compound. If you have all nonmetals bonded together, okay, electrons are going to be shared. Everybody's going to play and have fun. No electrons are going to be transferred. No tug of war. No one wins or loses. And we're going to call that a molecular compound or covalent compounds. They're so synonyms. Okay. These calculating the electronegativity differences they're kind of fun. They're just like a little subtraction problem. And usually it's what we call the absolute value of the difference. We don't care about sign, perhaps, as much as we do care about the magnitude of the difference. All right. So delta chi, change in electronegativity. And I already mentioned kind of the absolute value of. They only care about the magnitude. If you go ahead and go to that go-to slide, and I think you guys are going to have some homework that's due Monday after spring break. If you go ahead and atom A and atom B, and their electronegativities are the same, your delta chi will be 0. What if you have kind of a little bit, one's a little stronger electronegativity than the other, you have a difference of 0.5, difference of 1. Now here actually electrons are going to be shared all the way up to, and it depends on who you talk to, what time of day it is, but all the way up to electronegativity difference of about 1.2, electrons are still going to be shared but not shared equally. 1.7 electrons are transferred. So these first 4 I have listed are actually forming a covalent bond where electrons are shared, but they're not shared equally. Let's see, I don't have my slides in front of me, but can you guys help me out? Go a few slides ago when I had Pauling values, and can you tell me what the electronegativity value of oxygen is?
3.5.
Thank you. What about the electronegativity of hydrogen? 3.1, thank you. Okay, so between the two, actually oxygen has a stronger electronegativity. It will hoard electrons to itself. If I go ahead and take these two, I can actually calculate the delta chi, the electronegativity difference. And using that formula, it looks like this. Simply, it's 3.5 minus 3.1. You're looking at 0.4. Oh, thank you. All right. Yeah, that looks more like it, thanks. Right? So electronegativity difference, and that's describing the tug of war between this oxygen and this hydrogen that actually sharing electrons here. I say sharing because 1.4 still isn't up to 1.7, but it would be strongly polar. And the way we show polarity on this is to actually use, is it sigma? I got this wrong. The word is partial, and I can't remember which Greek letter it is, but this actually means partial, or like we're speaking Greek today. Okay, so I would actually say that the oxygen carries a partial negative, because it's higher electronegativity, and each one of the hydrogens carry a partial positive. Partial positive. So that's what we say, kind of the polarity of the molecule. So I've got some examples here. These don't have specific, my next slide actually has specific elements. But for in the case, this could be sodium chloride, where the big gold thing is your Cl minus, and the little blue thing is your Na plus. Electron was transferred. And they're kind of showing, instead of 1.7, they're kind of showing the cutoff is 2. So what are you going to do? If you look at A and B, your two atoms, and if their electronegativities individually are identical, their delta chi, or electronegativity differences, is going to be 0. And actually, when we look at kind of the gold represents the electron cloud, and in the middle there, you can't see it, would be the nuclei of A and B. But that electron cloud is distributed equally or evenly kind of between those two atoms to create that covalent bond. So that's actually what we call a perfect or pure covalent bond. This would be kind of as I've drawn it with my water molecule, or our water molecule up here. We said that electronegativity differences between the oxygen and the hydrogen, 1.4, not quite enough for an electron to be transferred, but your oxygen is going to be what we say electron rich, because it's higher electronegativity, and your hydrogen is going to be electron poor. So that's the partial negative and partial positive to show the polarity. Polarity. Okay, so sodium chloride, electrons transferred from the sodium to the chlorine, because chlorine actually has a higher electronegativity value. So don't let it get lost in this discussion. The arrows I showed you, electronegativity increases for group A elements, take the B's out. It increases from left to right, and electronegativity increases up the group. So kind of keep that in mind. See, a Cl2 molecule would be an example where both atoms have the same chi, the same electronegativity value. So electrons are shared equally, kind of shown there. And here's an example. If you look up the, well, go ahead. I have hydrogen. So what's the electronegativity value of chlorine?
3.0.
3.0. So if I'm going to go ahead and join a hydrogen and a chlorine, and I'm going to evaluate the electronegativity difference, it would be these two. 3.0 minus 2.1. Okay, so let's see. And chlorine has a higher electronegativity. So kind of what you're seeing there is this is partially negative, this would be partially positive. But electrons are being shared. to create that chemical bond between those two atoms. It's a subtle thing, but how we join these atoms together to make a compound is an important thing. So just to kind of summarize, I've got competition out there. Like I've been saying, if a compound's formula has a metal in it. Now, you might be like, well, what if a compound's formula has all metals in it? And that's kind of an interesting thing. And that happens with metal alloys. And I don't know if I can convince you, but if it has all metals, if you have like stainless steel, it's those individual metal atoms, each is homogeneous mixture like stainless steel would be of different elements, different metals. They're like stuck together, but they're not chemically bonded. They're like frozen. It's like a homogeneous mixture. So you really can't get metals to bond to other metals. But if it has a metal in the formula, then it's ionic. I've been saying that. And if it has no metals, if it's all nonmetals, remember hydrogen counts as a nonmetal, then your compound is a covalent compound. Yay! So this will be due. It summarizes what we've been doing. Okay? Cookies for the road, guys? So good.